How are we doing, everybody? Today we're in the third day of our interview session with Mirza, author of New Dimensions in Sociology, a Physico-Chemical Approach to Human Behavior. We're going to dig into Chapter 5, Affinity and Socialization, and go through today to the end of his book. And tomorrow we're going to dig into some of his new articles and look at some of his online citations where he's been having influence in the last 6 years, and then go back and look at a debate for 2 months we had when we first met online and rehash some of those discussions. Before we get going today, though, Mirza asked me while I was setting up the equipment, he says, was eoht.info my own creation? So I'm going to explain that a little bit, give a short history. So, for example, in 2016, 10-volume set of eoht.info, Encyclopedia of Human Thermodynamics.info was published as a 10-volume print set. And so where exactly did this come from? So if you go down here to where it says, this is a work in progress, online, 10-volume print set. You click on the work in progress here, and then you'll get you get a history of where this came from. So over here, this is me right here as a chemical engineering student in the year 1994 to 1995 at the University of Michigan. Everybody else was just trying to get a good grade and get a nice job in the chemical engineering industry. But me, I was thinking about things. I wanted to master the subject and understand all of the subjects in terms of what's called the Faustian quest for knowledge. That is, trying to understand the why of everything in terms of the big questions about human existence. And I really wanted to understand thermodynamics was the key for me in terms of opening the door to the world of answers. So here, somewhere in this range, in either Chemical Engineering 330, Chemical Thermodynamics 2, or Thermodynamics 1 in 1994, or Physical Chemistry, spring 1995, or maybe it was by the time heat mass transfer. Someone here had the idea of that the Gibbs free energy was the measure of the spontaneity of human chemical reactions was planted in my head, and I wanted to know how this applied to the spontaneity of human chemical reactions. So going forward, you see so right here, sometime in 2000, before I started chemical engineering, at about age 21, I wanted to know how you could match, in theory, a man is supposed to grow up in the world and be matched with a woman and have a family and grow old, get a house, have kids, grandchildren. So when you're a young person, age 15, you want to know how you're going to, what rules should you use to match yourself. So for example, and I know in Pakistan, I think Faizan was telling me that before the internet, people were pretty much matched up according to your aunts and your grandmothers would kind of match you with people. And then now with the internet, people are starting to meet other people through Facebook and social media. So back in when I was between 19 and 21, I wanted to know what the rules were for this. So I made Excel spreadsheet diagram of the top 19 girlfriends that I could potentially marry, and I listed traits over here such as Grambler likes her spontaneity, she has nice fun factor, hair, body, intelligence, character, class, and I ranked a point scale for each one, and then tallied each one, getting a value on the end here for the total points of each one. So according to this methodology, I should pick the person who has scored 140 right here, because she scores the highest according to my ranking methodology, which is this person. But the whatever the logic I was using, it wasn't making any sense to me. So then when I got to chemical engineering and I saw that reactions are matched like this, chemical reactions, A plus B goes to C, forming the child, the man plus the woman, it's all determined by the measure of the Gibbs free energy change. So if it's negative, that means that it's spontaneous, and nature favors the reaction. So if you choose that reaction, you're going in the direction that nature wants you to go. And if it's positive, that means you're going into an unstable or unnatural reaction. You're going to have to absorb energy from the universe to make it happen. It's going to have to be a forced marriage. And if it's at a zero free energy change, it's an equilibrium reaction, which means it could go backwards or forward. And it's kind of a neutral or ambivalent reaction. And so, Mirza, you agree with this kind of logic, don't you?
Mm-hmm.
What's your opinion of this sort of
Okay.
But so going forward, where UHT.info came from, I was confused. Technically, this is like what it's called. Goethe went through the same thing. He, before he wrote Elective Affinities, he wrote a book called it's called The Love Thought Experiment. He wrote a book called in October, in 1808, October 2nd, he would started writing a story called The Renouncers. And the story is that the man, the leading character, is a hero, and he's simultaneously in love with 4 women. And here's the diagram right here. So Goethe's over here, and he's in love with 4 different women, and he wants to know how you're supposed to choose which one you're supposed to marry, and if there's freedom of choice and there's no social constraints. So he was struggling with this problem in 1808, and then so by 1809, he realized that the best way to answer the question is through the chemical affinities, which is he said these are the chemical affinity reactions. We can determine through the reaction beaker which chemical is going to go with which chemical by the affinities in the reaction. And so he's realized that this would be a way to answer his question, not fully, but he wrote a novel called Elective Affinities, where he elaborated on this whole puzzle he had in his head about how a person is supposed to choose who he's supposed to associate with. And so that is called the Love Thought Experiment. So I ended up getting into the same. So we see right here in 1882, Helmholtz proved that the measure of affinity is free energy is the measure how we measure the affinity or the forces of chemical reactions. And he published this in his proof on the thermodynamics of chemical processes. And Henry Adams, who we talked about, remember when he started laughing about the phase diagrams, and he said, I want to pay a physical chemist to proofread my work. And he said, the triple point is coming, it's going to be free. You only take a few dollars. He had the same thought experiment. He wanted to understand hold on, maybe I have power problem. So So here we have Henry Adams, and he's married to Clover Adams, who he thinks is molecule A, and he's also he's confused about sort of another romance he has with molecule B. He calls it was Elizabeth Cameron. And so he's writing over here, he says that social chemistry, the mutual attraction of equivalent human molecules, is a science yet to be created. For the fact is my daily and only satisfaction in life. And he said this is a letter to Clover. It was right here. And he wrote this in 12 April 1885. And so the science he's speaking about that's yet to be created was first done with Mirza's book, which we're talking about right now. Mirza was the first one to publish an actual fully worked out model of the science that Henry Adams is talking about here. Because Henry Adams, once he started working on trying to understand this in terms of Gibbs free energies. And he hired Willard Gibbs' student, Henry Bumstead, to help him proofread his phase rule applied to history. But it started out as this kind of a thought experiment on how a person chooses different things in their existence. Well, then by the time I got into it here, I originally just did the thought experiment like this, but then I found that the free energy is the measure of the choice of the reaction, just as it is if you put hydrogen, oxygen, and sodium together. There's three elements. Nature's going to choose that oxygen will bond with sodium over that of hydrogen based on the chemical affinity of the three component molecules. And the change in that reaction is measured by the free energy in the system. So that's something I learned as a chemical engineering student. So the problem was So here we are. So this is the rule for spontaneity right here. So the change in free energy being less than zero on reactants going to products has to show a decrease or be negative. And this equation has to hold for any spontaneous or energetically favored reaction in the universe. So you agree with this, Mirza, that this applies at the chemical level and the social level?
Yeah, I put down quite a few notes in my book. Yes.
Okay, so Mirza, we both
very familiar with this one.
Okay, so but the problem for me is when I was a chemical engineering student, this all seemed fairly straightforward, but I wanted to know how you measure this enthalpy change and this temperature entropy change in terms of micro step-by-step interactions on going from, let's say, day one when a man is 15, he goes up and gets a job, and he finds a wife and has kids. So I wanted to know how the whole process of this whole thing works over this multi-year reaction. So it was very confusing to me. I wanted to know how I could do the derivation in terms of actually starting from the proof of this equation and going up and deriving all the variables. So I struggled with this from 1995 to 2001 just as a mental hobby. I would get up when I was bored or wanted to take a break, I would get out paper and try to do the derivation from the chemical thermodynamic equation point of view. And chemical thermodynamics has over something like 800 equations that are just your basic equations. So I kept struggling with this until 2001 when I started to see that if you have a hypothetical reaction where A man reacts with B, D, or E, three different women producing three different children, there's going to be each free energy change for each reaction. And this is going to be married out in terms of loosely, the one loose puzzle for me was reading Stephen Hawking's A Brief History of Time, where he talks about that when a person reads a book, he decreases the entropy of his brain or his system by by so many million units of entropy decrease. So I saw here that when you educate yourself, you're decreasing the entropy of your mind, and it's equivalent to a man getting a better job and becoming a high-ranking person in society. And once you're there, the idea of the women will naturally be attracted to the rank and the prestige and the money because it's a principle in the universe of energy flow. So there kind of gave me a handle on how you could measure this enthalpy and entropy change. But then he says, reading this book, Hawking will have increased the amount of ordered information in your brain. However, during the same time, heat released in your body will have had a much greater effect on increasing the disorder in the rest of the universe. So this principle isn't exactly right, as I've found from doing 20 years of research more on this, but it gave me a key into the puzzle. So then, this was a real turning point for me here. So now I saw that the entropy is a measure of randomness or disorder of a system, or kind of a measure of the order. And so here I saw that if I had three different entropies right here for the three different that increase in entropy of change over here. For this reaction, man plus woman forms the child, and I have four different enthalpy examples right here. I'm going from initial state to final state, that I have 5 different values of delta S, and I had 5 different values of T times delta S, and that the Gibbs free energy, if you add up all of these factors, is this negative 266 is the, let's see, here. So this trend right here shows that by decreasing the central nervous system of the male, you get a more negative delta G. And so this is the most favored according to your intellectual, or when you become a more organized person in society. And this trend right here, so this is the entropic factor, and over here is the enthalpic factor. So that by decreasing the physical, this gets into the physical heat, because enthalpy is generally thought of as the heat content of the system. So this is kind of the heat of passion between two people, and whether two people are attracted together in terms of physical heat versus mental heat. So this.
How do you arrive at these figures? 385, 355.
These are kind of just fictional figures that I made up, but I saw that whatever they're in the future, we'll be able to measure them. But I knew that there's going to be a scale. That are going to be so I picked numbers on scale, and I found that there'll be a change in the enthalpy, and then so here's the.
In my case, this delta H is internal energy.
Delta H, internal energy. Yeah. It's internal energy plus the.
Internal energy, then I interpret that internal energy in terms of resources.
Resources, yeah.
Yeah. So the resources are lost. Resources turn into entropy.
So the enthalpy is, for you, is a measure of the resources?
Yeah.
Okay.
Yeah. that goes into, that's how the entropy increases
Mhm.
and the resources decrease.
Okay. Yeah, that's good. That's good. Make sure you put that in the second edition of your book.
Yeah, yeah.
So when I type this all out later on, when I made a later version of it, here we see that
I've discussed that matter.
here we see that free energy when the enthalpy changes minus 400. We see the free energy when the enthalpy changes minus 250 for and we see the free energy change when the enthalpy is negative 100. So we see three different reactions. So this most negative is the most favored, and then we see the five different entropy entropy changes on this column, and this shows that when you multiply by the temperature of the system, that this is the different for 5 different hypothetical reactions. This is the most favored over here. So we see there's a way so you can microscopically see the. So this kind of gave me a doorway into the puzzle. So then, once I got this in 2001, I decided I wanted to research who else thought of this idea besides me, because before that it had just been my own creation of my own mind. So then I wanted to see who else thought like this, because originally, when I was
But you know what? This is a neat example of my hypothesis that life is entropy driven.
say what?
It is entropy driven. Entropy driven.
Entropy driven, yeah.
Yeah. Life is entropy driven. See, the entropy is increasing
Mm-hmm.
all the time, and the resources are decreasing.
Yeah, let's take a look here.
You have quantified it.
Yeah.
You have quantified it.
Yeah. So I made the, but this was in 2001 when I started seeing that I could make the table like this and see this is a change. So for example, let's say between this negative 310 or this 250 in enthalpy and this minus 400 in enthalpy, I understood that the difference between this enthalpy changes this enthalpy would be a change in the physical character. Say if you got in physical shape, or you got maybe if you got resources or something like that. Like say if you you grow and become very obese, you lose your physical attractiveness the same way the molecules lose their heat content. And then I saw that if you change your entropy, say if you become if down here let's say you're a homeless person or something, high entropy, just chaotic on the street, begging for change on the side of the road. But then you go to school, you start educating yourself, your entropy starts decreasing. You get yourself a nice house, your financial health is good. You become because each molecule in the universe has a measurable entropy and a measurable enthalpy associated, and this changes from state to state to state. So this way give me a way I can understand step by step in terms of daily mechanism how you can change your enthalpy and entropy, and this comes together in terms of the free energy reactions you have with different people, whether it's your potential mates or friendships or the society you bond to. So getting back to how I got to UHT, so in 1995 when I was listening to these lectures, I wanted to raise my hand and ask in the class, how do you apply this reaction socially? This is if chemical thermodynamics explains all these reactions in the beaker, who's the person who's done this sociologically? So then, after 2001, I started researching. So then first I found Goethe in 2006, and then in 2014 I found you. But before that, I had to research everybody, not just, and that's where the writing came from. So in 2005, I started, let's see what's on here, I started So this is one thing I did, and I needed proof to prove my theory in my mind. So this is where I got data. In 2002, I went to the University of Illinois. I was living in Chicago, so I went to the University of Illinois Chicago, And from all the graduates from 1969 to 1972, I took their photos of their male and female photos of everybody who graduated and the degree with which they got. So what I did was I had one group of people rank the physical attractiveness in terms of most beautiful and least beautiful in terms of their face on a scale of 1 to 10, or on a scale of 1 to, I think I used a scale of 1 to 7. And then I had another group of people rank the degrees they got in terms of intellectual difficulty. So there was about 120 degrees, going from easy degrees like psychology to hard degrees like engineering and mathematics and physics and chemistry. So these are more intellectual difficulty. So I saw this as a measure of, I correlated the data and found that over here that the attractiveness is inversely proportional to intelligence. And these are the data of all the plot right here. So right here, this is the data for female science majors from 2000, let's see, from the University of Illinois. There's P is psychology, B is biology, C is chemistry, M is mathematics, and there's 40, 20, and so if we look over here, we see that if you study psychology versus biology versus chemistry, and this is the attractiveness scale. So chemical women who study chemistry, and this is mathematics, there's 21 women who graduated with degrees in mathematics, but they have a physical attractiveness of 2.6, which means they're low in physical attractiveness, but high in intellectual attractiveness. Mm-hmm. So over here, we have chemistry. It's high in intellectual difficulty, because you're attracted to these smart people. Men are attracted to intelligent women. But they're also a decrease in the physical attractiveness. So then biology is easier degree, so more attractive women get this because they're already physically hot, but they don't need to work as hard to develop their intellectual attractiveness to get the same man. And over here, there's 41 women who got degrees in psychology. And psychology is a very easy degree intellectually on a scale. It's a 61 in terms of intellectual difficulty. So mathematics, people rank as the most intellectually difficult degree, near to chemistry. But so psychology is easy. So women who are high in 3.5 on the 7-point attractiveness scale, they're high in physical attractiveness versus, but low in intellectual attractiveness. So this showed that I could prove that attractiveness is inversely proportional to intelligence, or that enthalpy is inversely proportional to entropy. This is in a short summary of the situation here. So then you can correlate this. If you assume that enthalpy is proportional to the physical attractiveness, and entropy is inversely proportional to the intellectual attractiveness, and that this breaks down mechanistically like this, that the free energy change is equal to the enthalpy final minus the enthalpy initial, less the temperature of the system times the product of the entropy in a final state, less the entropy in the initial state. And this is the same way the enthalpy in a final state of the reaction energy barrier. This is the enthalpy in the initial state. Then you could plot that for this reaction here, if you have the Gibbs free energy final is the child at age 15, the Gibbs free energy initial is the reactants of the male molecule at -3 years before the child's born, and this is the Gibbs free energy of the female molecule -3 years before the child's born.